the single-headed attention RNN, or stop thinking with your head, making a simple, small, and fast experimental architecture based on RNNs that emulate our transformers. Now, why would we use anything that isn't a transformer? Well, there are a few issues. Transformers are generally very computationally intensive and quite memory intensive. Early attention layers also spend time looking at nearby tokens, such as the E and the looking for T and H, which means that really we're wasting a lot of computation when we have existing neural architectures such as the LSTM that work quite well for this task. Multi-head attention also perform many matrix multiplications, meaning that we generally run out of compute and memory, so we have to limit our context. And finally, transformers require a lot of compute in most applications, and they can be sensitive to initializations, learning rate scheduling, and so on. So we look back into the past, into the pointer-central mixture models by myself, Merity et al., and also improving neural language models with a continuous cache by Grave et al., to inspect and see whether or not we can improve the performance of LSTMs using even just single-headed attention and some more modern transformer techniques, such as throwing in the single-headed attention, a residual connection, and what I refer to as the boom layer, or a feed-forward layer where we take a hidden state from small to large and then back to small. So really, this is a very minor change to many of the existing LSTM implementations. But what do we gain from that? Well, LSTMs are still used in production as the models that we distill large complex transformer models into. So this is really an LSTM with a bit more optional. It backs off to an LSTM, so if you drop all of the past memory states, we still have the hidden state of the LSTM in order to produce more tokens. All of these components are also incredibly simple, meaning they're easy to export to, say, Onyx. And for any existing production systems that have been optimized for LSTMs, it shouldn't require a great deal of work to get this into production. And finally, simplicity means a new way to understand. So a simplified architecture helps potentially understand where some of the transformers' gains come from, because many of those are still not entirely obvious. So how does it perform? Well, first, we only train for less than 24 hours on a single GPU. Almost all of the existing transformer models don't offer that level of computational efficiency, except for the adaptive attention span transformer, which does, with only a single GPU and 24 hours, achieve quite a strong result. Even then, however, we're able to get incredibly strong results, beating out traditional LSTMs by a huge margin. 1.23 drops to 1.07 on the NWIC dataset when we're measuring bits per character. In comparison, the adaptive span transformer is able to achieve 1.02 with a slightly smaller parameter count. So whilst it isn't going to change the world, it is potentially going to change a few things. I think the single-headed attention RNN offers an interesting new model for distillation and also an interesting model to experiment and see where some of these transformer gains are actually coming from. Play around with it, see how it goes, and I'm excited to see what you're able to come up with.